Good afternoon, everybody. I am Evelyn Stock. I'm a cardiologist at UCSF and the co-chair of the Silicon Valley Bay Area University of Best Practices. And we are delighted to have you here today and being able to do these meetings virtually has actually the advantage that we can have speakers such as Dr. Alan Romali, who is joining us from NIH. Thank you for joining us today. So as we start our program today, we are going to hear about improving our cardiovascular risk prediction, Dr. Alan Romali, which is terribly important in the times that we're living. COVID-19 has, if anything, shown us lots of vulnerable spaces in our society and in our medical field. And as a physician, I have been incredibly challenged and grateful to have the resources that we have. So we are seeing in cardiology patients scared of coming to our centers, but at the same time adopting these new technologies that have allowed us to reach out to them and give them care. And without further ado, I will hand it off to Hattie to say a few words for today's program.
Well, I'm so glad that you were able to join us for even a little bit. I know you're probably going to be dashing off to do your next cardiology procedure there at UCSF Hospital.
I'm doing a TEE today, have to put on my full PPE. So I'm grateful I have that as well.
So maybe say just a couple more words about the kind of surge you're seeing that drew you into the hospital today. And I know Dr. Sky, who's with us from Travis Air Force Base Cardiology, expressed the same thing in just a few hours ago.
Yes, so as part of our mitigation strategy, so we could take care of the COVID patient, we stopped doing elective procedures for a number of months, at least 2 months at UCSF. They were only urgent procedures. So now we're seeing a surge in all of those procedures that we couldn't schedule before: echocardiograms, treadmill stress testing, and event monitors and things like that. So today I was going to originally be reading from home, but got called in because of the number of studies that are being needed and procedures as well. So I think we're seeing this at a number of medical centers. Our numbers are beyond what they were used to seeing before the pandemic, maybe about a 5% more. We're definitely back to baseline.
Wonderful. Well, thank you for coming on for a few minutes between your procedures, and thank you so much for recruiting your dear colleague, Dr. Alan Romali from the National Institutes of Health to be with us. Megan, would you please start advancing the slides? So I'm Hattie Hanley, and I'm the director of the California RightCare Initiative. We have built this collaborative across multiple academic institutions, departments of public health, health systems, and private sector health care entities for a dozen years. So next slide, please. I just wanted to share with you that we have so many wonderful partners from across the full state and increasingly even nationally, since our co-chair of our Capital Region group, Dr. Betsy Thompson, left her position as the Region 9 Director for the Federal Health and Human Services Agency to go off to be the head of cardiovascular for the Centers for Disease Control. So we're starting to do some work with our various leaders who've left for national positions, and it's a very exciting time to be freed up from our regional constraints, to be able to have such a wonderful speaker as Dr. Alan Romali coming in today. And in fact, one of his colleagues, the director of the Million Hearts program, Dr. Lawrence Sperling, will be our next speaker on August 10th. So the silver lining in the need to move to meeting by Zoom is that we can expand who is able to present to our group. So we've had more than 30 hours of programming since the pandemic broke out. And I think that the community is enjoying more than ever being able to come together to see each other and to continue to collaborate on solving this crisis. So I want to just say that without our volunteer leadership, such as Dr. Stock, Dr. Nurali Vorad, Dr. Bob Kaplan, Dr. Joe Skye, Dr. Bill Baumer from across the state, along with our financial supporters, this work would not go on. So I want to particularly thank the National Heart, Lung, and Blood Institute for being our first big sponsor back when we did our pilot in 2009 to 2012 and started our first regional community, where we showed a very fast reduction of acute myocardial infarctions, seeing 3,826 fewer AMIs than anticipated, and an $86 million savings with a $2.9 million NHLBI investment. So in addition to that, we've had lots of wonderful supporters along the way, including Blue Shield of California, who helped to start this latest chapter in the Bay Area, as well as Amarin, Amgen, Johnson & Johnson, Boehringer Ingelheim, Novartis, Genentech, Novo Nordisk, and the California Department of Public Health. Our most recent support coming in is from the Health Trust of Santa Clara. So with that, next slide, please. And you can just go through these real quickly, Megan. So I just want to say that we have not flattened the curve. This is what California looks like according to the Johns Hopkins website this morning, where we have a health crisis ahead of us that can partly be mitigated by better managing the #1 non-infectious disease killer, which is cardiovascular disease. It's what killed my mother when I was 15 of a stroke, and sent my father to bypass in his early 60s. Next slide, please. So I loved Dr. Evelyn Stock's discussion about, we're very, very focused on flattening the curve for the pandemic. And you see here, these are the Stanford University wonderful graphics about what's going on in our immediate Bay Area. And I would urge you to look at the beautiful work they have done in visualizing what's happening in the Bay Area and keeping such track of what's happening. But as you can see, while the shutdown has flattened the curve a bit for the COVID-19 pandemic, it's not in the shape of a mountain, which is what we would rather see. We're not there yet. We have quite a challenge ahead of us. So one way that we can address this is by, as Dr. Stock said on our call this morning, we need to flatten the curve for using everything we have for preventing cardiovascular events. Next slide, please. So this is a little hard to read, but essentially it says that hypertension is the #1 comorbidity, And Dr. Kane will be going into more detail about this later, but cardiovascular disease and hypertension are the major comorbidities for this pandemic. Next slide, please. Dr. Kaplan, thank you for your leadership and for being the one who wrote to the grant to the National Heart, Lung, and Blood Institute that started our regional work to implement in one place intensively the RightCare initiative strategies of controlling hypertension, lipids, and blood sugar through a collaborative approach in a regional setting. So with that, Bob, take it away.
Great, thanks, Hattie. So I have the pleasure of introducing Dr. Alan Ramilly, who is from the NIH. And Dr. Ramilly is, I believe, a native of Pittsburgh. He received his bachelor's, MD, and PhD degrees in biochemistry from the University of Pittsburgh. And then he went on all the way across the state to the University of Pennsylvania in Philadelphia to complete his residency in clinical pathology. And from there, he joined the NIH, where he stayed since he completed his residency, and went on to a postdoctoral fellowship in lipoprotein metabolism in the molecular disease branch at NHLBI. And he has a long series of very impressive accomplishments. He became the senior staff member in the Department of Laboratory Medicine at NIH, and he's currently the director of the immunoassay and special chemistry section. I won't go into all the details, but suffice it to say that he is a well-published author with more than 150 peer-reviewed articles. He has extensive editorial board experience in leading journals in his field. And he's a national leader in the area of lipid metabolism. So Dr. Ramilly, it's a pleasure to have you. And I just want to mention that before we get started, if you go down to the bottom of your screen, there's a little button for Q&A. And so during the presentation, if you as an audience member have a question that you want to ask, you can type it into that box, and hopefully we'll have time for regular exchange. But if it gets a little bit tight, we might be able to do some of the answers in a written format as well. And then we can prioritize some of the questions for the discussion. So with that, Dr. Ramilly, welcome, and thank you so much. I know it's a little bit late in the day for you, and we're glad to have you with us.
Yeah, well, thank you for the nice introduction. I'm happy to be here, and I'd like to thank Dr. Stock and Hattie for the invitation. And can someone put up my first slide? Or could I control it?
Hi.
I gave you remote control of my screen.
Okay, let me see.
I think you may need to share your screen, is that right? Or
yeah, just
There
hit
we go.
share content.
Yeah, I don't have a control panel on the bottom, but if someone, I could just tell people to advance the slides.
Okay, yeah, you just say next, that should work.
Okay, if you can open the first slide. That's the second or third slide, I think. If you can open the title slide. Okay, yeah, so Evelyn helped me make this title, and I added a subtitle, Back to the Future. I'm going to be trying to be the best I can, a little bit entertaining. I'm going to talk a little bit about popular movies, philosophy, and art, because the content is maybe dull for some of you. It's heavily dependent on math, but I won't go into that in great detail. The goal is to try to harness what we already measure and try to do a better job. That's why I was excited about talking about best practices. Most of the work I'm going to present has been published yet, except for the first work, which was published in JAMA Cardiology. And so I'm interested to get feedback from you. So if you go to the next slide, click again. So and one more time. So one of my favorite movies, and probably yours as well, is Back to the Future. And if you remember, Michael J. Fox goes back 30 years in time and to rediscover some things. And we're going to go back, if you go to the next slide, we're going to go back 50 years and click again. And we're going to go back to the time my predecessors at the NIH, click again. The person in the middle is Don Fredrickson, who was sort of my scientific grandfather. And he, a lot of the topics I'm going to discuss today, he first went over, again, over 50 years ago. If you click again, there's a few people that John Kane will recognize. Tony Gatto, who's still active and is in his 80s. He's the current president of the National Lipid Association, and Virgil Braun. If you go to the next slide. So I'm going to talk about a few topics. At the next slide, I'm first going to give everyone a crash course, literally just one slide on lipoprotein metabolism. Next slide. And then the three main topics are, I'm going to describe a new equation for how to more accurately calculate LDL cholesterol. Next slide. Then I'll talk about a new algorithm for lipoprotein phenotyping. And then finally, the next slide, I'll talk about a truncated risk score, which is not as good as the full risk score, but it's something that one can calculate with routine parameters, and I think potentially has great practical value in managing patients. So the next slide. So these are the pathways that have kept those of us who work in lipoproteins busy for many years now. And as you know, they're very circular pathways involving the liver. And even though we mostly talk about cholesterol, the reason we have lipoproteins is for energy delivery. And it's mostly delivery of triglyceride. And if you go to the next slide, so the left part of the slide has to do with two pathways, one in which dietary lipids is packaged in chylomicrons, and then you also have hepatic lipid or hepatic triglycerides packaged in VLDL. And these undergo lipolysis to produce remnant particles, and this is how energy is delivered or in skeletal muscle or storage in adipocytes. Now, if you go to the next slide, I'll talk also a little about HDL. HDL is still kind of a mystery. As you know, HDL carries a so-called good cholesterol and has many potential beneficial functions. What we think we understand the best is its role in cholesterol homeostasis, but I won't say too much about that today. Go to the next slide. So as I said, only the first part of this talk has been published. We published, I think it was in January this year in JAMA Cardiology, a new equation for LDL cholesterol that I'm very proud of. If you go to the next slide, and go to the next slide. So this paper was published in 1972. And it's one of the most highly cited biomedical literatures. It has over 100,000 citations because it was so important. It was published in Clinical Chemistry. And it described an equation which became known as the Friedwald equation. And it was based on about 400 patients seen at the NIH at the time that they used the reference method called beta quantification. And the reason it was so important is up until that time, there was no easy way to measure LDL cholesterol without doing this tedious centrifugation step. But they were able to, with a couple tricks I'll explain on the next slide, they were able to calculate this. And so it became known as the Friedwald equation. Friedwald at the time was a very young man. This is what he looks like now. And I think Don Fredrickson, who was a senior author, was always a little bit miffed, I think, that didn't become known as the Fredrickson equation. But it was named, it's based on the principle that lipoproteins are carried on just a few lipoprotein particles. Next slide. So they are either carried, if you have a fasting sample, so you don't have chylomicrons, they're either on LDL, HDL, or VLDL. Now, using selective precipitation, one can measure HDL cholesterol. So if one subtracts HDL cholesterol from total cholesterol, and then the next slide, the TG over 5 term is an estimate of VLDL cholesterol. So one can estimate or calculate LDL cholesterol by subtracting HDL and VLDL cholesterol from total cholesterol. Now, the weak link in which known even at this paper back in 1972 is this estimate. It's a reasonably good estimate, but you'll see there's lots of variation among the regression line that relates to TG to VLDL cholesterol. And because of this issue of accuracy, people usually don't recommend the use of Friedewald equation with TGs above 400. Now, people live with that for many years, and it's still the most commonly used equation. But now, as you all know, we now have PCSK9 inhibitors. It's not uncommon to have patients with LDL cholesterol well below 50. And those estimates using the Friedewald equation, you'll see, are wildly inaccurate. And a lot of patients are probably not getting appropriate treatment because of that. So if you go to the next slide. So this is something that you're all familiar with, the blind man, each with filling a different part of the elephant. And you know, the truth about this is that you need to step back to look at the big picture. So if you go to the next slide. So we did that too, both from like a metabolic standpoint, and also we used a different mathematical approach to come up with a better fit. So if you go to the next slide. So I got started on this based on a JAMA paper that Seth Martin and Steve Jones, who are two cardiologists up at Johns Hopkins, came up with about 3-4 years ago. If you go to the next slide. And it was quite an impressive paper. They had over 1 million test results using a technique called VAP, vertical autocentrifugation profile method. So it's a density graded centrifugation method, but it's not the reference method, and there are some limitations, but it's a reasonable method to separate lipoproteins based on density. And they developed what they call a new equation called the Martin equation, but it's really the same as the Friedewald equation, but they use a different estimate to divide TG. So if you go to the next slide. There's this table, and I think a very important contribution from Seth Martin and Steve Jones was the realization that not only triglyceride, but also non-HDL cholesterol, your level of non-HDL cholesterol changes the optimum factor. And it said for the Friedewald equation, you divide TG by 5, but you can see here, depending on your TG level or your non-HDL, you may want to use a factor 2 or use a factor much higher than that. So I, as you heard in the introduction, I'm a pathologist by training, and I was trying to implement this method in the clinical lab at the NIH. But those of you who are involved in clinical labs or any IT issues, you know how difficult IT is. And just to change a reference range, I have to beg and give chocolate bars to the IT people, and then I have to wait like 6 months. And most of the laboratory information software is very easy to implement an equation, but conceptually it's very easy to use a table, but actually to implement this using existing software, you have to have custom made lookup tables. So I immediately wrote Steve Jones and Seth and said, why not fit your table to an equation? It's much easier to use an equation than a table. And they said it was too complicated of a surface. So if you go to the next slide. So I was happened to be reading a biography about Enrico Fermi, and as you all know, is a famous physicist. And he was kind of unique because physicists come in 2 flavors. They're usually either good mathematicians or good experimentalists. And Enrico Fermi was actually good in both. And a lot of people would come to him with their problems. And so I didn't know this until I read the biography, but Freeman Dyson, who's a well-known mathematician, physicist, came to him trying to fit complicated data. And if you go to the next slide, and Enrico Fermi made this kind of snide remark about, if you give me enough parameters, I can fit an elephant. And if you go to the next slide, and you can fit any surface. The problem is if you overfit, many times equations aren't generalizable. But I took this up as a challenge, and I was able to actually, and I'll explain in a few minutes how I was able to do it. I was able to fit the surface, to fit the table fairly well. But if you go to the next slide, but another friend of mine, Jerry Segrist, who developed this method way back in 1980, go to the next slide, he had a word of caution saying that you should not use this method on high TG samples because chylomicrons are sticky and they stick to the sides of the tube. And Elliot Brinton, of the next slide, had a more recent paper showing that the VLDL is under-recovered by the VAP method. So even though they had 1 million test results, it is not the gold standard reference method, which is beta quant, and it's known to have a limitation on high TG. So I decided to go back to the beginning and use our own beta quant data. So over 20 years, we had about 20,000 beta quant results. And I decided to go and fit that data to LDL cholesterol. So if you go to the next slide. So the reasons for an equation, next slide. First of all, as I said earlier, equations are much easier to implement than a table. The next slide. The limitations of the VAP method in regard to high TG samples. The next slide. Anytime you have a table, it's by definition quantile in nature, so it's always a compromise, how many data cells. And then finally, as you may know, and I'll go over the new guidelines at the end of my talk, but one of the changes are that it's now permissible to use non-fasting samples. And so this issue of TG is a greater problem than maybe it was in the past. So if you go to the next slide. So Enrico Fermi said that you just can't simply fit equations. That's what he's telling his younger colleague. You have to understand the underlying physical principles. So I showed a picture of Tony Gatto around the table with Don Fredrickson. And Tony Gatto had a very important paper, I think it was 1974, where he applied for the first time NMR and lipoproteins. And he showed that they are like a micelle-like arrangement. They have a surface of phospholipids. Inside the core, they have the neutral lipids. And if you go to the next slide, so this paper was simply just they just used simple surface volume equations to describe a lipoprotein and came up with a mathematical model. And as you all know, to describe the volume of a sphere, you need to have cubic terms, and the surface area, of course, relates to the square. So from the very beginning, if you follow what Enrico Fermi's advice, one needs to use higher order mathematical terms in order to fit the equation, but no one ever did that. And I'll explain why in a second. So we decided we probably had to use higher order mathematical terms to come up with the correct equation. So if you go to the next slide. So the other thing that's always good, I always tell my students, you need to always look at the data. I mean, I'm not a statistician, and sometimes, when you don't understand it, you kind of assume it's correct. And I think you get a good sense of things by looking at real data. So we looked at our real data. So if you go to the next slide. So this is this is the data on about 20,000 results where we measured by beta quant the different lipids and measured, in this case, VLDL cholesterol by centrifugation versus triglyceride. And the colored dots are coded by their triglyceride levels. And you can see that there is a relationship between TG and VLDL, and the slope is about 5. But you can see there's a tremendous scatter about this line. So if you go to the next slide, but instead of color coding the dots by TG, if you color code them by non-HDL, you can see some patterns here. And you can see that there are actually curvilinear surfaces, and you can fit those whenever you have a single band, you can fit it ordered by a second order polynomial. So you have different bands of non-HDL that you need different equations. And this is what was apparent also from the table of Seth Martin. If you go to the next slide. So then if you plot non-HDL versus VLDL cholesterol, you get this very strange plot where you get this boomerang shape. And what it tells you is that once TG is at a certain level, you don't have an increase in cholesterol and LDL. All the increases is appearing on what apparently is VLDL cholesterol, but it's probably more accurate to say triglyceride-rich lipoprotein cholesterols. I didn't really get into it, but VLDL cholesterol sometimes is, or I'm going to use it synonymously with triglyceride-rich lipoproteins. These are particles that undergo only partial lipolysis and accumulate people with high triglycerides. And then finally, if you go to the next slide, I was aware of this, but I was not aware how striking this relationship is. And it's not apparent until you actually look at very extreme values. You notice that we had patients, many patients, in fact, that had triglycerides above 1,000. And when you see this very negative relationship between LDL cholesterol and triglycerides. And again, when triglycerides accumulate, LDL cholesterol goes down. And the reason is that the triglyceride, as the particles age, you have esterification of cholesterol by LCAT, and you have transfer of cholesterol ester into these particles by CETP. And then the triglyceride becomes more miscible and a binary mixture of cholesterol and triglyceride, and you have less triglyceride on the surfaces of those particles, and they can't undergo further lipolysis. So if you have old TG-rich particles that are sitting around not undergoing lipolysis, eventually they become impervious to further lipolysis, and these are what our remnants are. And these remnants actually are thought to be very pro-atherogenic, or they lead to triglyceride enrichment of LDL, which causes small dense LDL, and also TG enrichment HDL, leading to small dense HDL, both of which have been associated with cardiovascular disease. So if you go to the next slide, so basically, the reason people didn't do this before, I'm convinced, is that didn't use higher order mathematical terms, is that most people who are doing linear regression, they're trying to find the relationship between the dependent and independent variable. And when you do that, you want to have a simple equation, and you want to have higher mathematical terms, because you have this issue of what's called collinearity, which makes it very difficult to assign the relationship between the dependent and independent variables. But the other reason to do regression is to do a prediction equation. And when you're doing prediction, collinearity has no impact on that. But unfortunately, a lot of the statistical software won't allow you to mix terms like this. So we just did it in Excel. We made the terms that we wanted, and we picked the terms that worked. And so if you go to the next slide, so we found that there was a linear contribution of TG relates to VLDL. It was TG divided by 8 instead of 5. And that captures only part of the relationship. And then the next term, the next slide, and this accounts for the dotted line, the next slide. So you can see this here on the dotted line, but that relationship is affected by the non-HDL. So if you go to the next term is T triglyceride times non-HDL divided by this large denominator. And this adjusts for this linear relationship. And it accounts for the fact that you get enrichment of cholesterol by CTP. And if you go to the last term, it's next slide. Next slide. That accounts for this downward slope. And this accounts for the fact that nascent particles that are triglyceride rich are very poor in cholesterol. And only as they age, as I said earlier, they become rich. So this is kind of a correction in the term that accounts for this fact. So these are the terms that really allow you to get good fit. So if you go to the next slide. So here what we did is we made a contour plot where we plotted triglyceride versus non-HDL. The red represents the maximum level of the VLDL-C. So if you go to the next slide, this panel shows you what Friedwald says it is. And so Friedwald sort of gets the top right corner right, but it doesn't show this, you don't see this curvilinear relationship. You see this simple vertical lines. If you go to the next slide, this is the Martin table. So the Martin table is getting a little bit better, but it's still way off from the empiric data. And if you go to the next slide, this is our equation, and you can see that you have a contour, not identical, but similar. Now, we can actually match it better by using a cubic term. If you notice, I said earlier that you probably need cubic and square terms, but you have this issue called numerical instability. If you get too clever and you have these higher mathematical order terms, and you have noise in your system, you start amplifying noise. So we didn't use a cubic term, although it prevents that, it actually matches a little bit better. So if you go to the next slide, so we also looked at the beta quant. So here, this is the empiric factor value that they give you the best VLDL cholesterol, and red is a factor value of 20. So the patients with the highest TG but low non-HDL, you need factor values as high as 20. Patients with low TG and high non-HDL, factor values of 2 are sufficient. Now, if you go to the next slide, this just shows the two terms, and that doesn't work. Go to the next slide, and this is using the all three terms. We get a good fit. And if you go to the next slide, this is the Martin. The Martin is good in certain regions, but doesn't fit. So we actually fit the empiric data very well. So the proof is in the pudding, however. So what about VLDL cholesterol, which is the trouble that we have measuring? So if you go to the next slide, this shows the Friedwald fit. The dotted line is the regression line around 1. The solid line is the fit. So there's a slight positive bias, but there's a scatter throughout the line. If you go to the next slide, this shows the Martin table. It's a little bit better, but not much. And it has a negative bias. And then if you go to the next slide, this is our equation, and it fits remarkably well. You'll notice that we have triglycerides up to 3,000, but you'll see why, but we only recommend using it up to about 800 mg per deciliter, although it works reasonably well as all the way up to about 3,000. And the bottom panel is just the delta from the original value, showing in our equation that the errors are centered around 0. So if you go to the next slide, so what we did, the terms shown in red represent VLDL cholesterol, C represents total cholesterol, H represents HDL. So basically it's sort of like the Friedwald equation, but you notice that total cholesterol is not multiplied by 1, but it's by slightly more than 1 or divided by 0.948. So we did that to get a slightly better fit. So if you go to the next slide. So this is the fit. So the NH is, you can see this is on 20,000 results. These are color-coded by TG. And you'll notice that you get these nonsensical, go to the next slide, by Friedwald as well, the next slide, by Martin, you get these nonsensical negative LDLs, and some are quite extreme, minus 200 LDL cholesterol, which it's impossible to have a negative value. And that's because of the errors. And this is what I said earlier. Now that we're more aggressively treating patients, now it's possible PCSK9, people are getting scared away from treating patients because if you're trying to do a calculated LDL by Friedwald, you oftentimes will get the wrong value. So we largely fixed that. And in the paper, and I'm not going to go over it today, but I shared the equation with LabCorp and Mayo. Medical labs are 2 large reference labs. We shared it. Well, first of all, I should say we did not patent the equation. The Martin table is patented, so Quest bought it. So if you use their calculation, you have to pay someone. So we decided to release ours for free. So I gave it to both LabCorp and Mayo and anyone who wants, including you. And they tested on 250,000 people, and compared it to the 2 common direct assays. So direct assays can overcome some of the problems with the calculation, but they have their own problems and they cost extra money. And we found remarkable correspondence, you can see in the paper, with the direct assays on high TG samples. So I think the final slide on this is in the next slide. Oh, I have 2 more slides. So next. So here we plotted the difference between the true value as measured by the beta quant versus the calculation, our calculation in green, the Martin in orange, and the Friedwald. And over the years, there's been over 12 different equations have been proposed, and I listed them there. And you can see using all the data, we showed that the least mean absolute difference. Go to the next slide. Next slide. And this is on TG less than 400. There's very little difference among all the equations. There is a subtle difference you'll see in a second, but they all do reasonably well. Go to the next slide. And it's really the TG greater than 400 that you get the big advantage in our equation over the other equation. And if you go to the next slide, here we plotted the mean absolute difference against the TG for our equation in green versus the Martin in yellow versus the Friedwald. And you can see you're not supposed to use the Friedwald above 400, and you can see why. You get this huge error shown in the purple line. The Martin is better, but ours is, it also gets worse over time, but it's relatively flat. And in our analysis, the error rate the misclassification rate you get at Friedwald at 400, we approach that at 800 mg per deciliter. So we don't recommend going above 800 if you assume the allowable error of 400 was permissible. So that's why we came up with 800. And then I think the next slide is the last slide on this. The next slide. No, I got a few more. So yeah, so let's just skip this. Yeah, the next slide. And so basically what we found is, I said earlier, we did fit the Martin table. The problem with the table is that some of the number of patients in the different cells was low, so they had the wrong assignment. You can see by the different, the white, the next slide, you can see the 400 cell, and there's some other problems. Go to the next slide. The next slide. And what we found is that we were able to fit the Martin table almost exactly using the same mathematical terms in our equation with some slight adjustment to the coefficients. The next slide. But the Martin table is not properly calibrated for high TG, where ours seems to have good calibration across the TG range. But mathematically, our equation reduces to the Martin table at low TG samples. So the next slide. So this is, again, the final slide. So what we did is we calculated the misclassification rate using the three equations on patients with TG between 400 to 800 or low TG. So if you go to the next slide, so in the top box, I quantified the overall error rate. So you got 22%, which is much higher than I would like, but it's lower that's the rate that you would see with free roll at 400. So that's why we came over with 800 as a limit. And you can see that the Martin equation in the red box, they have a positive skew, and the free roll has a negative skew shown on the left. And the lower the LDL, you can see in the less than 70, they have a huge negative bias. That's why you get a lot of those crazy negative results. On patients with TG below 400, our equation and the Martin table give very similar results, but there's still an advantage, I think, for both our method and the Martin method over the Friedwald, starting at about 250 or 300. But you have to pay for the Martin table to use it, and the Martin table is not good for above 400. So if you go to the next slide. So, physicists are very clever. So it took about 50 years, but someone took Enrico Fermi's up on his joke, and using a trigonometric function and the math I don't understand, they were able to actually come up with next slide, using non-ideal numbers. They were able to come up with a 4-parameter equation, and the 5th parameter, they were able to wiggle its trunk. So next slide. So now my next parts won't be as long, but I'm going to talk about a new algorithm for lipoprotein phenotyping. The next slide. So this is another picture of Don Fredrickson in the top right-hand corner, and you all recognize Lyndon Johnson in the bottom left. And actually the patient on the bottom right is a young boy. Unfortunately, he passed away, was the first patient with Tangier disease that Don Fredrickson described. He came up, as I said, with the Friedwald equation along with Bill Freewall and Dan Levy. But the other thing that he's actually famous for is the Fredrickson classification. So to go to the next slide. So the Fredrickson classification at the time, electrophoresis was being used. I think they're using starch gel block electrophoresis, which I never used, but it would crumble. And he was doing that on every patient, and they were kind of very fragile. So he gave hundreds of these to the photographer in the basement of Building 10 at NIH and told him to take a photograph. And about 2 weeks later, the photographer came back with only 5 photographs. And Don Fredrickson, he told me the story. He said, no, I want you to take a picture of all of them. And the photographer said, but Dr. Fredrickson, there was only 5 patterns, because at the time it was actually, film was expensive. So even though Don Fredrickson missed out on the equation being named after him, he benefited from the photographer's insight that recognizing pattern, and it became known as the Fredrickson equation. And I don't think the photographer was actually cited on the papers. But this was very important because the hope was that these patterns would have underlying genetic causes. And it's true in some cases, but not in most cases. Most of these are best viewed as phenotypes, not genotypes. And this has caused a lot of confusion, but nevertheless, it's actually still important. And I'll talk about that in the end, why you want to determine these, but it's still very tedious. You can now we do agarose gel electrophoresis, or you can do beta quant or some other techniques. But if you go to the next slide, this was a next slide. So this was some famous papers that I'm sure John Kane is very familiar with, that inspired a lot of people. Almost the whole issue of the New England Journal of Medicine was dedicated to Don Fredrickson. He had like 5 or 6 papers describing each phenotype back in 1967. So over 50 years ago. So if you go to the next slide. So many years later, Alan Sniderman, who's a very well-known lipidologist up in Montreal came up with what's called the Sniderman classification using lipid panel results and ApoB. He was able to get the original phenotypes by Fredrickson, and he had a very good rationale clinically why you would want to get these different phenotypes, and I'll get into that in a second. And I like ApoB, and ApoB is actually important to measure, or you'll see it's actually necessary to identify some of these phenotypes. But unfortunately, it's an extra test, and it's not widely used. It's I think it's a shame. But I was interested in coming up with another classification that uses the tools that we have without using ApoB. So if you go to the next slide. So what I did here is I mapped ApoB versus triglyceride, which is the two parameters that are important in Alan Sniderman's classification, instead of using this flow chart. And what's apparent when you do this, you see there's some white holes, which is a problem from a classification standpoint. There's not a lot of people in some of these areas, but there are some, and he's not classifying them. And one of the things I enjoy is art. And so when I saw this immediately, this reminded me of Peter Mondrian, who's, of course, a famous Dutch artist. If you go to the next slide. And, he was always using these primary colors with white. Go to the next slide. And inspired, fashion design, the next slide, and all kind of crazy things. And the importance of his work is to understand the essence of, he was one of the first abstract artists. So we were trying to understand the essence of lipoproteins and why they align in these patterns, but I wanted to fill in the white dots, the white squares. So if you go to the next slide, next slide. So what we did is we used this well-known relationship between ApoB and non-HDL. There's a lot of scatter along this line for reasons I'll get into, but they are highly correlated. So as I said, I like ApoB, but a lot of people don't measure ApoB. But it does correlate closely with non-HDL. So if you go to the next slide. So here is our classification that's being reviewed on, at Journal of Clinical Lipidology, where we replace ApoB with non-HDL, and then we use TG. And if you go to the next slide. So the other thing I did is I used different cut points in Alan Sniderman. Alan Sniderman's cut points are largely based on the 75th percentile. And I think the reason he did that is what Don Fredrickson used in his classification. But I wanted to I went to the best I could to be completely aligned with our current guidelines. And I'll show those in a second, the 2018 guidelines on clinical management. So instead of using 133, I used 175 as my cut point. And this, go to the next line. And instead of 531, this is just a trivial change, I use 500 because the FDA will approve drugs for pancreatitis prevention at TGs of 500 or more. So those are two cut points that are well used. And if you go to the next line, as I said earlier, go to the next line, that if you have low TGs, your estimate of LDL cholesterol is reasonable. I do like non-HDL better, but again, I think the new guidelines, for whatever reason, they overemphasize LDL cholesterol, and almost all the current guidelines use LDL cholesterol. So we used the Friedel equation to solve for non-HDL using TG, and you get these diagonal lines. And that first top diagonal line that distinguishes 2A from NH, so NH stands for normal lipidemic hypercholesterolemia, or normal lipidemic high risk, is at 190 because that's the current guidelines say. The current guidelines say if you have LDL cholesterol 190, you want to treat those patients aggressively despite the absence of any other risk factors. The line at 160 is, again, the current guidelines say you use LDL cholesterol above 160 as a risk enhancer test. And I call those normal lipidemic high risk. N is normal lipidemic, and NL is, again, with the current guidelines say if you have your LDL cholesterol below 70, those people probably have low risk, which I don't necessarily agree with, but that's what the guidelines say. And so I use those points. If you go to the next slide, I will explain better the other cut points, and they're not really based on guidelines, except for the distinction between 2B and 4 is at a non-HDL of 220, and that's based on some old guidelines. So I tried to come up with a phenotype that is consistent with how we're supposed to practice medicine, at least in the US. if you follow the 2018 guidelines. And I then tried to phenotype them, and we validated these you'll see, by doing NMR and also doing beta quant and agarose gel electrophoresis on about 10,000 patients. So if you go to the next slide. So this is real data, plotting TG versus non-HDL, and is color-coded by phenotype. The dotted line represents the ratio of TG to non-HDL for pure chylomicrons. So no one has pure chylomicrons. Even patients with a genetic defect in lipoprotein lipase that have what are called type 1 hyperlipidemia, that have the highest TG, they still have some, they have HDL, although it's usually low, and they also have some remnants and some LDL. So no one falls that line. There are some people that fall on the LDL line, but no one, of course, has pure LDL, and the dotted line in VLDL. So it shows that the type 4, which is light blue, have enrichment in VLDL. So if you go on the next slide, instead of plotting instead of plotting the absolute, if you plot the log of TG, you see these purple ones at the bottom left. And if you plot the log of both, next slide, you see those ones at the very bottom, and they're clearly different. And so we call those type 6 hyperlipidemia. And that turns out we have probably the world's largest collection of patients with A-beta lipoproteinemia. Those are patients that have defects in MTP and have very low B-containing lipoproteins. And it's very important to recognize them because they go blind or have peripheral neuropathy unless you treat them with high-dose vitamin A and E, and one can identify them using our algorithm. And then if you go to the next slide, we instead of plotting the log or absolute, we plot percentiles. And when you do that, you can see why all these lipoprotein phenotypes align where they do. So if you go to the next line, the red patients are the 2A. Those are the people with high LDL cholesterol. And then the mixed dyslipidemia, the next line, are the browns. Those are people that have both high LDL and high VLDL. They have probably more LDL than VLDL. They have both. The next line, the kind of a gray, those are patients with type 5 hyperlipidemia that have also higher levels of VLDL, but also a little bit of chylose remnants, and they're kind of a mixture, and they're halfway between that. And the next line is the type 1 hyperlipidemia, which have more chylose than anything else. And the next line, the pink, are the patients that are normal lipidemic at high risk. The next line are the next slide are the type 4s. And then you'll see why in a second, we divided type 4 into two. Now that you have a lot of people, the recommendation is you don't need to fast. We find that you get a lot of people that have a type 4 pattern from non-fasting. We call it, in this slide, I call it intestinal hypercholesterolemia or 4B. They don't seem high risk. And those are the people in dark blue. So and that line, you'll see why we drew the line there. So if you go to the next slide. Now, one problem with my classification is you cannot get type 3. And the reason is type 3 is highly heterogeneous. The type of particle accumulates. Remnants are really a whole spectrum. And some patients, remnants of type 3, you have smaller versus large. And the ratio of cholesterol to TG varies tremendously among the particles accumulating in type 3. And you really need to have ApoB. So you have ApoB, and this is what Alan Sniderman always says, and it's true. You need ApoB to measure type 3. So if you go to the next slide, if you suspect type 3, they turn out to usually fall in the type 4 or type 5, but they tend to be scattered all over the place. So those patients, you really need to do ApoB or order agarose gel or do ApoE genotyping, some other method to pick them up. If you go to the next slide. But type 3, as you may know, is probably less than 1% of the population, but they're still important to recognize. And they do have some physical signs that might lead you to suspect type 3 as well. But one cannot get type 3 with our classification, which is one limitation. If you go to the next slide. Here, as I mentioned earlier, we did NMR on 10,000 patients, and we map the different things. The patients with the highest cholesterol, highest LDL cholesterol, those are people with large LDL. And those tend to be the type 2A patients in the top left corner. And if you go to the next slide, The medium LDL, and if you go to the next slide, is also there. And if you go to the next slide, the small dense LDL all appear in patients with type 2B and type 5. And you can see the line between type 5 and the one below we call IH. If you go to the next slide, that was kind of a break point, next slide, in ApoB. And you'll see that patients in the lower type of type 4 have, I think, are non-fasting individuals or for whatever reason don't seem to have high risk from MESA. So if you go to the next slide, here is using our phenotyping classification. And other people have reported this, largely Alan Sniderman, and I think John Kane believes this too. But type 2B is a very dangerous thing to have. Even though there's a lot of emphasis on 2A, those patients with type 2B, many times they're ignored or undertreated, but it's a very aggressive disease. And in MESA, the patients with the type 2B, actually by our phenotyping classification, seem to have had a very high risk. The type 2As are in red. And the ones with the lowest risk, oddly enough, were the patients with the type 4B or the intestinal hypertriglyceridemia, which seem to not to have high risk. Now, if you do the same classification with the Sniderman classification, next slide, you don't get as good of a separation. And I think that's largely because he uses 75th percentile and he kind of lumps together more normal lipidemic individuals. Now, if you and again, the other nice thing, the thing that I like about our phenotype, and we are aligned ourselves with the current guidelines, you'll see in a second there it provides trigger points for doing other things. Now, if you go to the next slide, the phenotype is highly significant in predicting future cardiovascular events. However, if you go to the next slide, if you put in lipids, it disappears, and that's because the phenotyping is dependent upon lipids. So it doesn't add value in predicting future cardiovascular events because it is dependent upon lipids. But if you go into the next slide, we have, this is just an abbreviated table, but we have a very complicated kind of algorithm where we kind of recommend that you need to have referral to lipidologists, or you need to order ApoB, or that you should consider other drugs besides statins. We kind of use the state of the art to say that we have actions for each of these things. Like type 6, you really need to refer that to a lipidologist. You need to have a nutritionist. You need to do high dose vitamin A and E. So we try to have things that require action. And so this is not to help lipidologists who know how to do all this, but it is to help other clinicians who are seeing these patients, and probably even cardiologists who are usually very knowledgeable of lipids, but may not be knowledgeable on some of the genetic dyslipidemias. So if you go to the next slide. So the very last thing, and I'll try to accelerate, is this new truncated lipid risk score. And the idea behind this was there was great reluctance, I remember about 10 years ago, and we got a lot of pushback in the clinical lab when we started offering estimated GFR. Some people said, well, there's an equation for it. So they didn't want to clutter the lab report. But it turns out, people who practice medicine now, who grew up with it, would seem that that's foolish. And the estimated GFR is very important because people always don't understand, what is also an issue with COVID-19. They don't understand logs and exponents. So slight increases in plasma creatinine oftentimes are ignored, but slight increases mean you're on your way, potentially. Many times people attribute that to lab error, and the plasma creatinine measurements are usually very accurate. So slight increases usually start accelerating because it's an exponential relationship, and people ignore them before it's too late. And so that's the whole point of the estimated GFR. And in order to do estimated GFR, you need the plasma creatinine, and you need age, sex, and race. So what I'm going to show you is that I like the full risk score that Peter Wilson developed, but go to the next slide. Next slide. So when I talk to my cardiology friends and I ask them about, do you use the full risk equation? And some of them do, but many of them said they don't, or they don't be troubled by it. It's not actually hard to use, but you need to collect the information. From my talking to them, I realized that it's too hard, even though it's conceptually easy, people aren't using it. So I wanted to come up with something that maybe is not as good, but something that we can actually calculate and that would add value, and also see when you needed the full equation. So if you go to the next slide. So these are the current 2018 multi-society guidelines from ACC and HA and NLA. And this is only for primary prevention. So as I said earlier, go to the next slide. If you have an LDL cholesterol greater than 190, you don't need to do anything else. Those patients are high risk. They for sure need to be on statins. Everyone else between age 40 and 75, the next slide, you go down this pathway and you are supposed to apply the full ACVD risk equation and then calculate the 10-year risk, and you stratify them, except if their LDL cholesterol was below 70, they have low risk, you don't need to go further. And then you use a risk enhancer test to decide how aggressive you should be. Okay, so if you go to the next slide. So this is the risk equation. As I said earlier, it's sort of like the estimated GFR. It all depends on using logs. And it's much more complicated because you have 7 different parameters, and there's also a lot of interaction terms. You can see the second term here is log of age times log of total cholesterol. And there's not something you can do in your head. And some people who see a lot of patients probably have a good sense of the risk, but I'm impressed when I ask people, and I actually quizzed people and gave them a little test. A lot of people don't do well on this test, and you can see why, because mathematically, it's kind of difficult to wrap your head around this. And furthermore, to make it even harder, you have different equations. There was a big advance. You now have separate equations for men versus women and African Americans versus non-Hispanic whites. So if you go to the next slide. So here, I started out, but you'll see I have a better way of using it. My first goal was to come up with an equation that would not use LDL as a strategy to triage patients. So right now, you're kind of triaging patients. If your LDL is greater than 190, you don't do anything, you know, high risk. If LDL is below 70, you don't have to do anything else because they're low risk. And I was skeptical of that because the problem is calculating LDL. And I was right to be skeptical here using NHANES, which, as you know, is a general population study that's about 10,000 people, was meant to match the US general population. I calculated here both the sensitivity and specificity compared to the full risk equation for identifying low risk and high risk patients. And you can see that has either poor sensitivity, poor specificity. And because some of these high and low risk groups aren't that prevalent, as clinicians, you really want to know, instead of sensitivity specificity, you want to know what the positive and negative predictive value is. And you can see it's quite low. So I wanted to improve upon that. It was my first goal. So if you go to the next slide. So here, I assumed everyone was a 65-year-old white male. And I did this because if you don't do this, it's very hard to see patterns. But what you see here, I calculated, and it's color-coded by the 10-year risk score, that patients with both the highest total cholesterol and the lowest HDL, because those are the 2 lipid parameters that are used to calculate risk, total cholesterol and HDL, have the highest risk. It's just not total cholesterol. It's both parameters are almost equally important because it's in the top right-hand corner. So if you go to the next slide, this is just a contour plot of that. It's just easier to see. So if you go to the next slide, we made several other contour plots of other lipids. First of all, we use LDL. LDL tends to peak, as I showed earlier, in the top left corner. If you go to the next slide, non-HDL is a little bit better, but not perfect. Doesn't quite fit the pooled cohort risk equation. If you go to the next slide, ApoB is not a big improvement. And triglyceride actually fits the best. If you go to the next slide, but triglyceride has a tremendous biological variability. It's over 20%. So it's actually probably a better predictor if you can measure, if you didn't have that biological variability, but that really dampens the ability to use triglyceride as a risk predictor. So if you go to the next slide. So here we did ROC analysis, which is just, as you probably all know, measures sensitivity and specificity. Again, assuming in this case, they were all white males, age 50. And we looked at the different lipid parameters. LDL cholesterol turns out to be one of the worst parameters you can use. And some of the ratios of like non-HDL to HDL were better. But as soon as you start adding back real risk, so in the second column, if you go to the next slide, Next slide. So if you see here in the second column, what we plotted here is the area under the curve. You can see it, a test that has no prediction would have a ROC score of 0.5. You can see it deteriorates tremendously if you start adding real risk factors. If you go to the next slide, if you add true race, age, sex, and all true risk factors, it's actually very hard to see the contribution of lipids to risk, because quantitatively, almost all of us will get heart disease sooner or later. We might not die from it. And age is by far the most important factor. So age, sex, and race are very important. You need to adjust for that. So basically, we decided to come up with an equation using age, sex, race, and the 2 lipid parameters, and not use blood pressure, diabetes, cigarette smoking, and blood pressure meds, because we don't have that information in the clinical lab. So if you go to the next slide. So this I showed you earlier. And if you notice, it looks kind of messy, but it's the sum of the exponents of the log transform data. That's all it is. So basically, we took that term and that exponent, and we did linear regression, and we took out the terms we didn't have, and we adjusted the coefficients for the terms that we did have, and we got a remarkably good fit. If you go to the next slide, where we try to match. Go to the next slide. Where we try to match the full equation shown on the X versus the truncated NIH risk score, and we got remarkably good fits without the missing information. So that was very encouraging, and we got it for the 4 groups that we're trying to study. So if you go to the next slide. Next slide. And here we showed on the left is MESA, 5,000 patients, where we looked at the full risk equation, and brown are the patients with the highest risk. And you can see that the risk equation did separate, did predict long mortality. But you can see our truncated risk equation also predicted fairly well. However, some of the patients with the highest risk moved into the blue or the intermediate risk, because we don't know their blood pressure. So they may have been high risk, but we don't know their blood pressure, so they didn't have the highest risk. But you can see, nevertheless, we were able to have good separation. So if you go to the next slide. Next slide. So here we showed that if you don't know, if you calculate our risk using our truncated risk in blue, and then you discover someone has diabetes, if you multiply by 1.6, you end up getting almost the same result. Smoking, you have to add about 2% risk, almost regardless of where you are. Blood pressure meds had a very little effect. The factor that we're missing, that's the most important, that we don't have in our full equation, is systolic blood pressure, and that's a continuous variable. So that's the part that we're really missing, and that's why our truncated risk equation cannot be as good as the full equation, because blood pressure is important. So if you go to the next slide. But you can see here, compared to red, which is using LDL cholesterol, using the current guidelines, using LDL cholesterol below 70 versus greater than 190 to identify low and high risk patients, it doesn't work. But you can see, using the blue line, using our truncated risk equation, we can identify those patients very well. So if you go to the next slide. But then I had this revelation. So this is Doc Brown from the first movie. And I had a revelation that I was asking the wrong equation, the wrong question. If you go to the next slide. So I was excited that we could, people on the extreme, we can do better, but that's not where the money is. The money, where most people are in the middle of the distribution. So instead of using our truncated equation to look at the extreme risk, I asked the question, can we use a truncated risk equation to identify people that have intermediate risk using the full equation, that have intermediate, which is defined by a 7.5% 10-year risk. So if you go to the next slide. So basically, again, I went back to N. Haynes. I calculated the true risk using the full equation, identified the true negatives and true positives. The next slide. Next slide. Next slide. And then I came up like the weatherman does. A lot of people just use a single cut point, but by sliding the cut point, we can have different degrees of certainty. And you'll see in a second, I converted that into positive and negative predictive values. So if you go to the next slide. So this is the real data using NHANES, using true negatives and true positives and applying our truncated equation. And you can see there's this overlap, but there's a fair amount of separation. And if you go to the next slide, and you can see that even at the middle of the distribution, we had a great ability to identify patients that had a 10-year ACVD risk. So these are patients that are statin eligible. So if you go to the next slide. Next slide. So here I converted it to negative and positive predictive value. And this is our truncated score. The next slide. The next slide. So just from a lipid panel, age, sex, and race, which are parameters that the clinical lab has, we could identify half of all statin eligible patients, knowing nothing else. And the reason I think this is important is that despite the emphasis on the guidelines, only 1/3 of people who are eligible for statins are on statins. That's probably true for many reasons, but part of the reason is people aren't following the guidelines. And yeah, as you probably all know, patients now have easy access to their own lab report. And if some, not all patients, but some patients, if you tell them they're statin eligible, they will make sure their doctor gives them statins if they are eligible. So I think right from the beginning, by not doing the full equation, we can identify half of all statin eligible patients using parameters just from a lipid panel. This, again, this is just for primary prevention. So if you go to the next slide, next slide. So 40% of the population, if you have a truncated risk score less than 2, the negative predictive value is 99%. So I'm not against the full equation. I think everyone should probably get the full equation, but if you don't want to do it, you probably don't need to do it for this group. The next slide. If you have between 2 to 4%, the negative predictive value is 84%. So I would say here, maybe it's optional, but the next slide. Next slide. But if you have a truncated risk score between 4 and 7.5%, you have about a 50% probability of having it. And it all depends on whether you have hypertension or other risk factors. So for sure, those patients, you need to do the full equation. If you're lazy, you don't do anyone else, you need to do it on these patients. And in the lab report, we can indicate and have a link and say, you need to plug in these other values to calculate the full equation. And I think this will improve compliance. Again, I'm not against the full equation. The full equation is better, but people aren't doing it. And I think this might prod them to do it. Now, if you go to the next slide, you don't really need it if you're above 7.5%, except for maybe looking at statin intensity, which if you follow the guidelines. So if you go to the next slide, go to the next slide. So the next slide. So you don't need it here. Oh, just skip this. Just click, 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 click. Okay, so I think you got it. Okay, so I probably tortured you long enough. So I'm going to stop here and just give a few closing remarks. Okay, so next slide. So in summary, next slide. So using just results from the standard lipid panel, but using higher order mathematical terms, it is possible to more accurately calculate LDL up to TGs of at least 800 mg per deciliter. And that's been published. We did not patent it, and I'm happy for anyone to use that. Several large reference labs are using it now, and NHANES and on the new release of data, they're actually going to use the new equation. Go to the next slide. Again, using just results from the standard panel, it is possible to phenotype patients for lipoprotein disorders, except for type 3. And I didn't really get into it, but I think this information is not maybe useful for lipidologists, but it is useful for everyone else in helping clinical management of patients. If you go to the next slide. And finally, using just results from the standard panel, you can also come up with a truncated lipid risk score, which is very similar, as I mentioned, to the estimated GFR. And it can be used to detect the maybe not the great majority, but at least the majority, at least half of all statin eligible patients. And by using it, I describe, it can maybe perhaps increase compliance with statin use and compliance with the use of the full equation, which is better than my truncated equation, but people simply aren't using it, and they're just kind of going on their own sense of someone's risk. If you go to the next slide. Again, this is all just using results of the standard of pound. I'm not talking about using another test. I do like ApoB myself, and I'm not against ApoB, but the current guidelines don't recommend it. And all this is just using things we already have, just making better use of the tools that we have. So if you go to the next slide, so in theory, this should represent a low bar for implementation. But in practice, as you know, non-HDL is also free and is a great way to help. And people just don't use it. So I don't know if some of these ideas will be implemented. That's why I was excited to talk to you today, because I'm hoping to get have people kind of use these tools. I'm convinced they will add value. So if go to the next slide, which I think is my last slide. But you know, in the clinical lab perspective, we have to be careful how we do this. So we want to nudge people, but we don't want to kind of bother them with, you know, trivial stuff, you know, we call the feather statistical insignificance, or be overly paternalistic and force their hand. If you go to the next slide, you sort of have to kind of nudge it and do it right and have common sense. And that's why, again, I'd be very interested either after my talk here or later for people to give me feedback. I'm not personally see patients, so some of my ideas perhaps are foolhardy. So I'd be very interested in your feel how this could be used. So if you go to the next slide, these are some of my colleagues at the NIH who helped me on various aspects of the study. Maureen Sampson, I highlighted in red. If you go to the next slide, this is a picture of Maureen and me, which we call the so if you're going to call it the Sampson equation, even though I wish it would be called the Ramallah equation, but because of the story of Friedwald, I think it should be named after the first author. So this is Maureen, who's a med tech, and she's really a whiz with computers and a whiz, and I couldn't have done it without her. And if you go to the next slide, this is my very last slide. It's my I talk about rediscovery, and so I thought I knew, you know, everything to know about the Friedwald equation and Phenotype, but you know, I've only been the work I showed you is stuff I've been doing the last maybe 3 years or so. But it wasn't until actually I started digging into it myself and trying to make it better that I think I now understand it. And so that's, you know, that's a whole process of rediscovery. Sometimes it is good to go back. And now that I'm, you know, I've been doing this now for about 30 years, I go back and read papers I read when I started my career or stuff long before I started in this business. And I get stuff, I see things differently than I saw the first time I read it. And that's really the whole, that's why rediscovery is important. You see things differently second time around. Okay, so that's my talk, and I'm sorry if I went a little bit long, and I'd be happy to answer any questions or to talk to any of you offline and or send any of the free software that does all these things to you at any time.
Thank you for sharing your incredible work. Dr. Kaplan.
Yes, thanks so much, Dr. Ramley. And I think that we probably need to go on to Dr. Kane, but then we're going to come back for a general discussion in just a few minutes. So hold on, and for those of you that want to ask questions, there'll be two ways to do it. One is by raising your hand under the Participants tab, but you can also type a question in under the Q&A tab. So with that, I'd like to introduce Dr. John Kane, who's an endocrinologist from UCSF. Dr. Kane has been good enough to come visit us in the RightCare initiative previously, and he gave a fantastic talk on lipid metabolism just, I think, a couple months back. He is a internationally recognized scholar and has contributed in a wide variety of ways to the field. He's received the Outstanding Achievement Award from the International Atherosclerosis Society for his works on the genetics of lipoprotein metabolism. So with that, Dr. Kane, thank you so much for joining us, and then be thinking about your questions, and hopefully we'll have an opportunity for a robust discussion after this presentation.
Well, this is a pleasure. First thing, to follow this impressive re-examination of the mathematical relationships of lipoproteins, because we've been, the field of cardiology has been essentially operating on 1970s insights for all the time. And I think that I have no slides. I'm just going to talk from ideas here, because I think we're in a new space, and I want to mention that. And that is, I'm going to start by a clinical observation. And that is, the first patients I ever saw with homozygous familial hypercholesterolemia were a brother and sister, each of whom died on reaching the age of 11 from an acute myocardial infarction. Imagine that. I'm going to, in contrast, describe a lady I'm seeing now in the clinic. She is a real homozygote. She has no response to PCSK9 or statins. We have her on apheresis, but for her whole life, she has maintained an LDL cholesterol about 1,000 milligrams per deciliter. And she's now reaching the age of 82, and she's had her first angina. I think there's a great deal of biology we have to learn to understand the difference between those two unfortunate little children and this lady who's been able to essentially ignore this extremely severe hyperlipidemia for all these years. So I want to go back and think then together with you all, because I think we're in a new place now, understanding why some patients have much more risk than the others, and potentially entirely unexpected new interventions. One issue that I think I would raise is that of LPA. LPA is a distinct lipoprotein because it contains the little a protein. We have no idea why this evolved about 80,000 years ago in our ancestry. Higher primates have it, monkeys don't. It's obviously contributes materially to risk. It has an effect which we were able to demonstrate with European collaborators of actually producing abnormally structured thrombi. They're resistant to plasmin, and so I think this is an independent contribution to risk that we have to understand much better. And I think perhaps everyone here is cognizant of the oncoming antisense oligonucleotide management. Preliminary studies look as though we can get about 80% reduction of LPA with no apparent side effects. So I think this may contribute materially. And it's our impression in our clinic today that about 20% of people have a significant elevation of LPA, chiefly people of Northern European ancestry, Northern India, and so on, this is a significant contributor to cardiovascular disease, stroke, and that this should be measured on every patient, just as the lipoproteins are measured now by others. And so there are, I think, going to be many other biological differences of lipoproteins. We now have a large number of apolipoproteins, which are represented in different species of lipoproteins, and we think quite differently among people. Certainly, apolipoprotein C3, angiopoietin proteins, including angiopoietin C, and a number of others. So I think the landscape here is going to expand, and ultimately it may be important to measure these other elements. But I'd like to move to another space, and that is conceptually, we have for the last 50 years thought a great deal about the accumulation of lipids in the artery wall. And a great deal of attention has been paid to regulating been given to regulating the lipoprotein species, identifying which ones are more atherogenic than others. And, but there's another complete dimension to this process of atherogenesis, and that is the efflux of cholesterol from the artery wall. And so this is an area that was investigated by some investigators at the cellular level, pure biochemistry, really with very little connection to clinical arteriosclerosis, until we began to look in our laboratory, and some of our colleagues otherwise as well, at the molecular processes involved, focusing on the emerging molecular species of high-density lipoproteins. And very quickly, certain processes have become apparent that are important. And I think that our discovery of the pre-beta-1 HDL, now supplemented by many other laboratories, really coming together to understand this process. The efflux of cholesterol is mediated by several proteins that have been identified already, involving apolipoprotein A1, certainly ABC, A1, LCAT, other contributors here. But in essence, what's emerged is that our pre-beta-1 HDL molecule is the acceptor of the efflux cholesterol. And we have been able to develop very accurate, reproducible techniques for measuring pre-beta-1 HDL. And I give credit to Dr. O'Connor from Ireland, who spent, Tricia O'Connor, spent several years in our laboratory. We invented the technique for measuring this. Now there are several others that are much more facile, but all of them together are very informative. And what we've learned is that the patients who have very high levels of pre-beta-1 HDL in plasma apparently have those because of impaired efflux. This is the acceptor molecule, and if you're not supplying cholesterol for the pre-beta-1 HDL to accept, then it accumulates, and you get very much higher levels of pre-beta-1 in plasma. We are about to submit a paper on 2,500 patients using the O'Connor-Kane technique, and we are getting hazard ratios from 2 all the way up to 4 in some subpopulations, but 2 is the minimum. Well, this is highly significant. This is equivalent to, p-values out the window. And so I think what we're looking at here is a second space, a new dimension that really is going to have to become part of the evaluation of risk. You can talk in detail about levels of atherogenic lipoproteins, but here's another whole aspect. Some people do not efflux cholesterol as well as others, and that's a very important contributory factor to the accumulation of cholesterol in the artery wall. Well, this has led us to investigate HDL speciation. We think there are about 25 molecular species of HDL in plasma, and they are very different in their makeup. There are almost 100 proteins among the 25 species. And to give an example of how they are important in other dimensions of biology, one of those species contains endotoxin binding protein. And we were able to show with a wonderful work of several of our colleagues here, Joseph Rapp being the leader of that. He's now a professor of surgery, UCSF. And what we were able to show was that this species of HDL can can bind endotoxins in the face of gram-negative infections and actually prevent death in animal models. So this is a very protective role. The endotoxins are transferred from this HDL species to triglyceride-rich lipoproteins, which hang on to the endotoxins. When they get to liver, the remnants are giving up their triglyceride, and at a point they yield the endotoxins to the liver, which transports it across the cytoplasm and puts it out in the into bile. And so that's how we have one newly discovered protection mechanism against endotoxins involving two species of lipoproteins. Still another defensive activity. We found a few years ago protein in HDL that had never been seen before. And we isolated it, finally called it ApoL because we were that far down the alphabet. And with wonderful investigators in Belgium, left over from the Belgian Congo, we were able to demonstrate that it is the protein that kills the organisms, the trypanosomes, that cause African sleeping sickness, a disease that kills about 12,000 people a year, mostly children in East Africa. So that is developing into a field of its own. I think that protein will be developed as a therapeutic for people with trypanosomiasis. We've now cloned the genes. There are 6 human ApoL genes. The products of 2 of them have turned out to kill viruses, HIV, and it's not reported yet, but poliovirus as well. So HDL species are doing a lot of things, and with about 100 proteins there, we are just beginning to understand those processes. So I think that another realm that is opening up as well is genomics. And we started out in this field with wonderful collaborators in industry, reported 27 gene loci where mutations are associated with increased risk of coronary heart attacks. And I think we had 7 for stroke. One of those proteins was VAMP8, which I think is so significantly connected with risk that it should be part of the workup for coronary vascular risk. So essentially what is coming together here then is I think that we need to advance a composite determination of risk. I think we're in a new world in this area. And I would suggest that certainly Dr. Ramali, representing the NIH, would be a great collaborator in this, as would this organization, which we're addressing today. Maybe some supporters from major university centers. But I think it's time for us to construct and project a composite risk determination involving, yes, very much more sophisticated analysis of lipoprotein particles. They really have disparate metabolism and pathophysiology that we need to be aware of. But we also need to measure pre-beta-1 HDL. If it has hazard ratios of 2 and more, that's highly significant. As those are the people who may look normal otherwise who can't efflux cholesterol. We also should examine the endotoxin content of lipoproteins. I think that there will be forthcoming other molecular species of HDL that are very important, and those are yet to be determined, identified, but I think they would contribute to this composite analysis of risk. But I think it's time to include the genomics as well. We have very important insights that are coming. A number of genes. If we have 27 genes, different gene loci for myocardial infarction, it's time that we put those into the analysis. We just this last week have received an acceptance of a publication with our collaborators at the University of Western Ontario, Rob Higley and his colleagues. We have found a new gene for profound profound hypertriglyceridemia. The proband for that discovery of those patients had a triglyceride of 7,000 milligrams. And so I think it's time for us to put forward a much more comprehensive assessment of risk. I think these are now, genomics is becoming very much less expensive with targeted genes. And I think that this is a time where our predictivity for risk is much greater. And I think we'll find some people who have a normal appearing LDL, who have something drastically wrong with efflux or other aspects, genomic aspects of intra-articular disease. And another dimension that we're adding in our sphere here is cytokines. We have now a panel of 65 cytokines. We have papers that are about to be submitted demonstrating that this really adds to the prediction of risk. There's some people with very different inflammation in the artery wall, and some of that's genomically determined, maybe also by other means that we'll discover. But we are putting these risk factors together now, and we have a paper just being submitted demonstrating that by using machine learning that we can analyze 75 individual cytokines with their interaction with each other and with now HDL species, and we are getting profoundly improved predictions of risk. Hopefully these findings will be published imminently. So I think we are moving into a new place where the combined biological insights of inflammation, genomics, speciation of HDL, efflux, the molecular distinctions of LDL and VLDL species could be put together to vastly improve the prediction of people at risk and discover some people who by conventional means would not be felt to be at risk, but who may be at profound risk, like the two little brother and sister pair that I encountered earlier who succumbed at the age of 11. And so I think I'm really proposing that the NIH, our university, other universities with insight put together a composite risk determination, and that this would go forward in cardiology as the new aspect of risk determination. So I'll accept questions at this point.
So is Ed on? Ed, Dr. Yu, are you on?
Yes, I am. Thank you.
Great.
And I believe Nirali is on as well. Dr. Vora, would you care to perhaps start your video, and are you able to be with us now?
Yeah, I'll just be on audio, however, but I wanted to thank the speakers. I'm sorry I came in a little bit late after my clinic, but thank you for sort of sharing these innovations with cardiovascular therapeutics and thinking about the brave new frontiers that are forward ahead of us and kind of getting out of our own regular box. I guess we can start the discussion. I know that there was one question that was raised in the chat box by Carlin Long. And Carlin, are you able to verbalize your question, or shall I read it for you? If you want to unmute yourself, it might be more interesting.
I don't think that I have the ability to do that.
Oh, we can hear you. Yes, please share your question, which was for Dr. Just for our first speaker, Dr. Ramali. Oh, he's centrally muted. Okay. So his question was, essentially, can you comment on the ethnic and racial subgroups and how the equations for cholesterol might, and for risk prediction impact, how these equations impact depending on the race and ethnicity? And did your equations do better in subgroups that were maybe not the 65-year-old white man?
Yeah, hi, thank you for the question. Yeah, I'm not sure if I maybe completely understand, Carlin, but as you may know, the reason for the 4 equations is that it was known for some time that men and women, differ in terms of the cardiovascular risk contributions. And unfortunately, a lot of the studies were only using non-Hispanic whites or Caucasians. And the same is true that various ethnic groups. And so I think as we go forward, we'll have more specific equations for each race and ethnic groups. Just for example, African Americans, lipids aren't as important. They are important, but not as important. It seems that on average, blood pressure is more important. And so they have the weight, the value of the coefficients terms different. And in some cases, like in women, they have an age square term, which affects the postmenopausal risk. Women, as everyone probably knows, tend to have low risk until the postmenopausal state. So that's the reason for the different equations. My truncated equation, if you're referring to my ACVD risk, it works reasonably well, but does not work better, as I said earlier, than the full equation. The full equation has more terms, so for sure it's going to predict risk better. Our truncated equation works reasonably well for the 4 groups. We did not have as many data points. We used NHANES. NHANES is a big study, about 10,000 people, but there were not that many African Americans, and so we didn't have enough data to fit that equation as well. So our truncated equation does not work as well for African Americans. So that's my answer, if I understood the question.
Am I unmuted now?
Yes, you are.
Okay, so sorry. So Ellen, I had thought that you had presented that your truncated equation did better when you looked at those other groups, given that they were not included in any of the previous trials that helped with the cohort equation. But what I hear you saying is that your NHANES data was probably no better in terms of its representation, and so you could not make that claim.
That's correct, yeah.
Okay, thank you.
I'd like to make a comment, if I may. Can you hear me?
Yes, go ahead, Dr.
Yes.
Kane, and then we'll have Dr. Baumer make a comment afterwards.
Yeah, I think, almost everybody in this field sort of refers to African Americans as a distinct ethnic biological group. But now that we're collaborating with people in Africa, I'm impressed with the fact that people in East Africa and people in the Congo and so on are extremely different, probably more different from each other than Norwegians are from Greeks. And we're very impressed with it. I think we're going to have to find markers that tell us really which subpopulation we're talking about, because they are biologically very different. And I think it's time to stop collectively referring to African Americans, we're I think, going to learn some really important differences biologically, and maybe we better become more sophisticated in that respect.
I had this is Bill Ballmer, I had a quick question for Dr. Kane. One of them was, I agree, and I think we all agree that composite risk would be the best thing to achieve. And the earlier clinically that we can identify that composite risk, the better off our patients would be, meaning if we can intervene and reduce that risk at age 20 throughout their 20 to 60-year-old, then we could prevent a lot of disease, rather than today we often wind up seeing patients at 60 or 70 years of age with disease, and then we try to intervene much after the fact. And so the influx of cholesterol and lipids into the blood vessel and the efflux or lack of efflux for that have been occurring over years. So the earlier we could achieve that, the better. And it seems that your recommendation of genomics might be a way to identify that early. But we also know with genomics that the penetrance of some of those genes from a variety of other gene effectors is not 100%. So at what age would you recommend that we have enough information now to do a genomic score on an individual such that we might preempt the development of atherosclerosis?
Well, I'd like to start by acknowledging the potential for gene-gene interaction. Certainly, this is pretty widely experienced in human genomics, that some genes will influence other ones. But I think that, you know, our genomics is assayable in childhood even. So, you know, I think that this is something we could be applying very early, and certainly earlier interventions are more likely to be clinically effective.
Thanks to both of you. I guess I want to take this opportunity to just comment. You know, we are talking a lot about biology and innovations, but at RightCare, you know, part of it is also reaching the broadest group in order to reduce preventable cardiovascular deaths. And I think that, you know, in the context of the current discussions about systemic racism in our country, and we're talking about biological groups, I do think it's important to remind ourselves that in addition to biology, there are a number of social determinants of health which are just preventing individuals from races and from Black race and from our Black community to access a lot of healthcare. And so that we can't lose sight of that as clinicians as we channel forward and incorporate the great biological data. So I just wanted to make that comment, since we're discussing this, that it all goes together. And we can discuss that as well. I do see one hand raised, Ramiro Zuniga. I don't know if you still have a question, and we can unmute him. I think you've been upgraded to a panelist, so you can go ahead and ask your question.
Sorry, I raised my hand by mistake.
Oh,
I do not have a question. Thank you.
No
So,
problem.
Nurali, this is Bob. I do have a question.
Yes.
I was just curious about this. Since since age remains the overwhelming predominant risk factor, I was wondering about where we are with lipid-lowering therapy for people over age 75. There was the Lancet piece a year or so ago that suggested that there's big benefit, but actually, if you look carefully at the data, at least for all-cause mortality, there doesn't seem to be much of a benefit. And I was just curious where the current thinking is on that.
I think that's a good question for both of our panelists. Who wants to take it first?
Well, I'll defer to John. I think, you know, what someone said earlier, that, you know, the current recommendations are kind of agnostic. You know, was that I went through that algorithm after age 75 in part because there was not a lot of data. There's some data, but maybe not enough to make a decision. And as John said earlier, or someone said earlier, the later the later you intervene, the less likely you'll be able to impact. But maybe John could elaborate. But I know there is some data that not only the vasculature of the heart, but the vascular of the vessels that feed the brain, and so dementia. So there may be reasons to intervene in older age groups, but I think there's not a lot of data, and of course, there's more likely of getting some of the negative consequences of drug therapy in that group. So I don't think there's a good, clear answer, not that I'm aware of. I don't know, John, do you have more to add?
Well, I think, you know, there's another dimension as you get older here. Lipoproteins transport beta amyloid, and it crosses the blood-brain barrier. And, you know, there are other biological interactions that we need to think about here. And that's becoming pretty important in our society as more and more people get older. So, you know, I think we probably, there's no reason to think you can't make interventions later, but the earlier you make them, the more likely they are to be effective.
Great, thank you.
Hey, good afternoon here. This is Ed Yu. I do also have a question for Dr. Amali again. Thank you very much for taking time. Great talk. So I represent a large integrated health delivery system in our geography. So my question regards about the implementation, and in particular about influencing the labs that report these values. I was intrigued by the notion that the way how calculated LDLs are calculated are somewhat owned and decided by the reporting lab, and the idea that you could patent a calculation to calculate that it was kind of news to me. So the fact that your score is in the public domain, I'm just really curious about, from your experience, how easy or how hard it is for labs to adopt that. And then with regards to clinicians' acceptance of that, how would having that in your approach endorsed by the existing medical societies, that this is a improved methodology to do so before we can see widespread adoption and implementation of this? So look forward to your comments. Thank you.
Yes, yeah. Yeah, I was surprised too when I learned that the Martin equation was patented, and as I think I may have mentioned in my talk, Quest Diagnostics, which is one of the large reference labs, purchased from the researchers at Johns Hopkins the rights for that patent, and I believe Quest is actually using the Martin equation or table to report LDL cholesterols. And I have lots of close contacts at Mayo Medical Labs, and they looked carefully also into implementing it, and they thought the improvements were marginal, but then there was the issue of payment. Now, I think, you know, because the reference labs compete with each other, it's likely that Mayo would have to pay Quest to do it. But in theory, I think smaller academic labs or smaller hospital laboratories may have to pay. You know, there was a lot of debate, like BRCA mutations in breast cancer, you know, whether one can patent, because there's different ways to do the sequencing. So there's a lot of uncertainty about this issue. And that, however, uncertainty creates, I think, disincentives in order to use it. And particularly if people are worried that some later date, 5-10 years down the road, they'll get sued for using an equation and not making a payment. The payment's probably relatively small, but it adds up if you're doing it for everyone routinely. So I had discussed this issue with my technology transfer. And when I came to NIH in 1990, there was no such thing as a technology transfer office. It's probably true universities as well. But at that time, we were actually, there was a lot of reasons of disinhibitions to patent And so the NIH didn't patent anything. Then they realized that unless they patent some things, it's clear who owns it. No one will be develop it. So in the late 90s, Harold Varmus, I believe was the director at the time, said it was permissible to patent. But in general, the NIH, since we're a public institution paid by federal tax dollars, we make a distinction between tolls. Like, so if I have a new drug, the NIH does patent, although they tend to give it away for a small amount of fee. But equation is considered a toll. So the NIH philosophy is they would not patent such a thing. So that's why we didn't patent it. Getting back to what you said earlier, so in 2018, I think that paper by Seth Martin, the first paper came out maybe in 2016 or so. So in 2018, the American College of Cardiology endorsed the Martin equation and recommended it to be used, particularly in patients with low LDL cholesterol. My paper only came out in January, so I'm hoping it catches on and that, you know, I will get some endorsement. But I'm also realistic. As I said, I think non-HDL overcomes some of the limitations of LDL cholesterol, and it's also a simple calculation. But a lot of people don't use it. Labs are encouraged to report it, but a lot of them don't. So even things that make sense sometimes don't get utilized, and it takes a lot of people publishing lots of papers, and you know, as I said, and if there's extra cost, that's oftentimes a killer. You know, I have a lot of friends who are in the health supplement industry or making healthy foods, and people surprisingly will spend very little extra to have something that's a higher quality food. I think because a lot of people don't have the luxury of spending more money. So it's hard to even convince people to do something that's for free that's better. So that's why I was excited about the opportunity to talk. That and you know, if any of you are listening or interested in using or trying to assess in real life the value of some things I described, I'm very happy to try to help you do it.
I'd like to comment that our immediate experience now with machine learning is so incredibly impressive that I think we're going to move to a new place in this field, incorporating better ways of looking at LDL cholesterol, better ways of incorporating other risk factors to where our predictivity is many-fold what we have now.
All right, we're nearing 6 o'clock. I guess Joe Sky has the last question. Joe, do you want to unmute yourself and ask it yourself?
Sure, Dr. O'Malley. I didn't hear you comment, and maybe I missed it, on direct measurement of LDL. How would that change things from your perspective? Is it a cost issue, or is there other factors?
Yeah, I guess maybe 10, 15 years ago, people developed what are called direct tests. Not all, but virtually all the direct tests were developed by various Japanese diagnostic companies. And I took a careful look at them at the time, maybe 10, 15 years ago. There were 7 or 8 of them. And we split samples and sent it to the CDC where they did the beta quant test. And many of the direct tests, they were designed using normal lipidemic individuals, and the reagents they use that either shield or selectively extract cholesterol from the different lipoproteins don't work as well as soon as you have some dyslipidemia. But they have improved considerably over the years, and several of the assays I do think overcome some of the limitations of the free world. And so many laboratories actually reflex to a direct test if someone's not fasting or if someone has a triglyceride over 400. But as you said, they cost extra. So the typical cost for the reagents for direct tests are on the order of about $10, and then the cost to the patient is higher than that. So many laboratories don't use the direct LDLs. Most clinical laboratories, however, have switched to the direct HDL tests. I think analytically they're a little bit better, but the previous way of measuring HDL required a manual precipitation test that cost labor and was more expensive. So the direct HDL tests work a little bit better, and they cost less than the way we used to do it. but direct LDL tests have not really fully penetrated the market because of the extra cost. But there is some concern about some of them. And as I said in our paper, we looked at the two common direct tests, are one by Roche and one by Beckman. One was done by Mayo, one was done by LabCorp, and we tested over 250,000 patients using the direct test, and we showed good correspondence with our calculation. So LabCorp, or I think it was LabCorp, is actually going to change their practices, and they are actually have already launched our equation and are now going to use less direct testing. So direct test has some value, but we'll see how it all works out.
So to clarify, you believe your equation is producing results that are as clinically usable, if not more clinically accurate than the direct testing, at least certainly previous generations of direct testing.
That's correct.
Thank you.
And again, I want to thank both of our speakers, Dr. Kane, Dr. Romali, for joining our talk today. Thank you for pushing us and thinking about, your innovations and what's on the horizon. At this point, I'll pass it over to Hattie Hanley to discuss the August program and our transition to our celebration.
Oh, I want to really thank both Dr. Romali and Dr. Kane for opening our minds to some new ways of thinking, very different perspectives coming from each of you, and yet I know there's so much common ground. I absolutely loved John Kane's challenging us in his own way toward getting serious about the challenge we have made for several years to create a get to zero equation. There are so many preventive approaches that are simply not being deployed. And that's what the RightCare Initiative is about. It's about taking what we know and even taking it from places as far and wide as National Heart, Lung, and Blood Institute to try to speed the adoption of clinically relevant best practices to slow down and prevent heart attacks, strokes, heart failure, diabetic complications, just using what we know, implementing it. So we really, really appreciate that. One thing that happens with the RightCare Initiative is other good things are catalyzed. And one of the things that we catalyze in addition to best practices is the growth of young healthcare leaders through the RightCare Initiative. Brian Vong grew up at UC Berkeley, really graduating there 2 years ago and staying with us for 2 gap years and being with us for 2 years prior to that. So Brian Vong is a very promising upcoming medical student at the University of California, Los Angeles, and he will be doing a joint master's program. He's not sure what the field will be yet, but it strikes me that given his joint work at the UCSF labs with Dr. Stock and Dr. Kane, and this inspirational lecture by Dr. Romali today, perhaps Brian Vong will be inspired to do his master's growing out of his very hard science background at UC Berkeley. He's been an absolute joy and delight over the last 4 years working with the RightCare Initiative. And I am going to turn over the microphone to my co-founder and one of my favorite colleagues I've ever had, Dr. Steve Shortell. Steve, can you join us by video now?
Sure. Can everybody hear me okay? I think I'm unmuted, Hattie. Thank you for that. And again, thank you, John and Alan and Joe and everyone else for the session today. I have not been able to make many of these. I got in at the tail end of this discussion and found it very, very stimulating. It's been a long road, thanks to Hattie and a number of others. We're at the beginning. as well. Want to recognize Bob Kaplan, I think is on, Arnie Milstein down there at Stanford also, Alan Fremont. We miss Alan a lot, but these are some of the people early on to bring the expertise and try to move the needle and prevent unnecessary death and morbidity. But I really want to call you out, Brian Vaughn. You're going to receive the first inaugural Rising Star Award. And for those of you who may not know Brian, I'm going to say a little bit about him. He's a Berkeley undergraduate, but he's been with RCI, I think, Hattie, for 3 years now. 1 year as an undergraduate, 2 years, the past 2 years, the gap year. He's the one that really puts a lot of the analysis and report writing behind all the briefs that you guys see. And with the summits that we've had, I think we've had 10 or 11 summits. Brian, along with others, but really led by Brian, has done that. He takes fairly complex data and writes it up in a very scientific way, but also transparent that can be understood. And I think, Brian, that gift and talent and skill is going to serve you well in your medical career also. I would also add a personal note that in some of the presentations some of us make at these summits and elsewhere, the technology inevitably fails. And maybe Hattie's up there, or I'm up there, or somebody else is up there, and we're all getting nervous and in a tizzy. Brian's the young man in the back of the room usually, comes up with a smile, very calm demeanor, and fixes the problem. And that attitude or whatever predisposition is also going to serve you very well in your clinical career. I just want to, if you don't mind, Hattie, read one thing that Hattie wrote about Brian, which I think sums it up, in a letter she wrote for his medical school application. And I quote here, "Brian is extremely bright, talented, dedicated, ethical, and a joy to work with, both in leading projects in teams and in his dedication to the public good." And I think, Brian, that really sums it up well. We're all very proud of you. I would just add that the success of RCI, the Right Care Initiative, you have very much put your own stamp on that. And my hope for you would be every success as you go down there at UCLA. Learn, just be a sponge, but also you're going to be a real terrific opportunity for learning on the part of others, which you're going to be able to share with them. And I think my hope would be after you get done with the next 4 years or 6 or 7 years, depending on your specialty and the residency and all of that, that you'll come back to Right Care. And who knows, maybe you'll succeed Hattie by then, right?
Absolutely.
So again, congratulations on the behalf of all of us. You've been a real inspiration for us. Thank you.
Thank you so much. To you, Dr. Schertel, and everyone else on this call. And I think to just do a quick transition, yes, thank you for the slides. Just wanted to highlight and share with you all that are on the call today, really some of my contributions to the Right Care Initiative, and really touch upon more so the lessons learned, and really have this opportunity to thank very personally all the mentors and all of the physician leaders that really have contributed to my personal and professional growth, and really what I consider really my success throughout the Right Care Initiative. So if we can go to the next slide, please. And so how I really describe my time at the Right Care Initiative, these past 4 years really has been an absolute journey. With my early beginnings with the previous research assistant, Amanda Liu, with working with Professor Brent Fulton at UC Berkeley, and really getting acquainted with the Right Care goals. And it was from those early beginnings to really working with Hattie and our team to really begin coordinating our University of Best Practices every month for 10 months out of the year, and really begin taking on more research responsibilities that I began to really get to meet some of our fantastic leaders here on the call and across the states, including Professor Jan Hirsch, including Dr. Bill Baumer and Dr. Marin, Dr. Budoff, across the board, across the state, to really produce these actionable briefs that really, in my heart, I've come to see are really the core to what we want to achieve, which is to improve the lives of others and to prevent unnecessary deaths. And really, as we go on, as I went on through the years into 2018, 2019, until now, really having the ability and opportunities really to work with Hattie and our team to lead more of our research efforts, really begin our newest University of Best Practices in the Bay Area, as well as collaborating with the California Department of Public Health to working with partners in Santa Clara County. So it's been an absolute journey. And if we go to the next slide, just highlighting some of those accomplishments really on one slide, including all 65 of these University of Best Practices, imagining just the wealth there. And as Hattie has mentioned previously, really a mini med school where we have lectures on a variety of topics, from lifestyle change to the more scientific lectures regarding lipids, or more of the community interventions from different medical systems in the area. Being part of and leading 3 summits, and really as we look at more broadly, what I've helped contribute really is, as Dr. Shortell was mentioning, these project briefs that I've worked with different physicians and researchers to produce, really in order to reduce death disabilities and really meet the Right Care initiative's mission. Go to the next slide, please. And so on the screen right now, just a little compilation of some of the briefs that I've worked with Hattie, with Dr. Susan Ivey, and many others from regarding the statistics for health, for heart disease and stroke in our different hotspot communities, related to coronary artery calcium, related to having pharmacists on the care team, all of which has really contributed to my lessons learned. So if we go to the next slide, if I were to summarize these past 4 years into 4 bullet points, it's really seeing that being evidence-based and sharing best practices really guides quality improvement in population health. As we sit in a room together on a monthly basis, we really come together and strategize how to best compete against disease and not compete against each other, in the words of Warren Barnes. Next, really the collaboration, the networks that we build in and out of our university best practices are really the foundations and the drivers for change, both on the local and larger community level. Really understanding the importance of intervention and prevention, understanding the science, understanding the very human side of health, understanding all these facets, and really how to begin bridging these many different silos in order to achieve our common goals. And really lastly, as I do a lot of the research behind the scenes, how to use data to share a compelling narrative, to really begin to build a coalition of allies, and again, further meet our goals. And really, all of these lessons that I've learned throughout my time at the Right Care Initiative really facilitated by many of those on the call today. So if we go to the next slide, I wanted to give a big, deep thank you to Hattie Hanley, to Susan Ivey, for really facilitating my growth, and with your mentorship, really showing me what public health, what healthcare really is about, what it needs, and the directions that make me very hopeful in my future career as a physician leader, not just a physician. Wanted to give also a specific shout out to our university best practices leadership from across the states, the RightCare staff, and really all of you on the line today, from our previous speakers to our current attendees. Huge thank yous. And the big question is, where are we going from here? Where am I going from here? If we go to the last slide. As Hattie and Dr. Chertel had mentioned, I'll be going to UCLA for their for a joint degree program that will allow me to receive my MD, but also have a special emphasis on leadership and advocacy through the PRIME program, really to address healthcare disparities in medically underserved populations in California and beyond. So again, wanted to thank all of you for the opportunity to work with you and take away so much these past 4 years.
Thank you, Brian. We do have leadership from around the state, and just to be fair, we listed them on the agenda, which we could actually bring up. I think we might start with Dr. Kane, because not only did Brian work for the RightCare Initiative, through the RightCare Initiative, I met Dr. Stock, and we were able to arrange that Brian would also work at the UCSF molecular cardiology lab. And I think he's had a fantastic experience working with you, Dr. Kane, if you'd like to say a few words about sending Brian off.
Well, it's with a lot of enthusiasm for what I know his career is going to come to, because he has certainly been among the most talented that we've had. Intellectually, conceptually, but also he's dedicated, and it's obvious that this is deeply embedded in him. And so we are just wishing him the greatest adventure going forward, because I think that's the way he sees it. And I'm sure he's going to have a genuine impact on the practice of medicine and on people as individuals.
Thank you, Dr. Kane, and also wanted to thank Dr. Carlin Long, also from UCSF.
I'm
Brian,
just
this
a money man.
Brian, this is Bob Kaplan. I'm going to have to run in a minute, but it's been a pleasure working with you, and I wish you the best of luck at UCLA. Of course, one of my favorite places. Make sure you do look at the School of Public Health, and I'm sure you're going to have a great experience there. So thanks.
Thank you.
I'll join in the Stanford comments. This is Nirali Vora. Brian, I just met you only recently in the last couple years when I was first invited to speak at one of the summits, annual summits, and I think Brian very calmly and in a very well organized manner was able to facilitate that talk. But since then, as everyone has said, I've seen his leadership, his poise, his intelligence, his passion in helping to start this great Bay Area University of Best Practices. And I think, Brian, you're someone who can always be relied on, and someone who knows how to do what's right and follow through. And those are going to be critical skill sets that are going to help you succeed as a physician and as a healer. And I think that's just so wonderful that you have the science background and you have the organization, but you have that compassion and humanism too.
Well, not that we want to actually get his head any bigger than it is already, but I would just second that what John said, and that is really that, you know, Brian has been such a joy to have around. He has integrity, he has honesty, he's organized, and you know, this is again one of those individuals that 20 years from now we'll all say, oh yeah, I knew Brian back when, and then you fill in the blank. So Brian, all the best, and of course you'll keep up with us, I'm sure.
I'm pretty sure he's going to be the one that unites all the UCs plus Stanford and USC, all of which are collaborators of ours, but we could be doing a lot more than we are. And one of my dreams is that that would include something where the medical students and the pharmacy students are directly involved. So keep dreaming big. And with that, let's go to our chairman of our capital region, Dr. Balmer.
Well, Brian, I'm happy to be here today. I noticed that in your background for your Zoom, you have a photo of the Golden Gate Bridge. And I thought it's appropriate because in RightCare, we've been trying to use equations to get to zero. And so I was going to offer you the equation for the catenoid shape, which is the shape of the Golden Gate Bridge for the suspension, which we found in an early publication. We showed that the catenoid shape was mimic the shape in hypertrophic obstructive cardiomyopathy. So that, again, was your way to get an equation into your final remarks. But I have another equation for you, and that is the RightCare Initiative success. So RCI, or RightCare Initiative success, equals BV to the fourth power. So why is that? Well, BV is Brian Vong, and to the fourth power means that your 4 years here have been exponential in improving the success of the RightCare Initiative. So you have, and we have derived an equation that actually explains and mirrors the success that you've contributed to the organization over the last 4 years. But maybe equations are too hard to push at this point, at this late hour of the day. So let's turn to something more mundane. That is, let's turn to the fact that you are going to UCLA. So UCLA, who is the mascot for UCLA? Well, the original mascot for UCLA was a cub bear, meaning that they were the junior partner of Berkeley, or UC Cal Berkeley at the time. And so they initiated the mascot as the cub. And this parallels your position and your evolution as well. You started out with RightCare as really a cub just out of school at the time, and you have evolved. And what did the mascot at UCLA evolve into? But into a grizzly at that point. And so you have matured from a cub scout in the RCI institution to a grizzly, where you were now responsible for putting slides together and other things. Now, I should mention that when we ask you for things, it's always at the last moment and with high levels of technology required to put that together. And I have to remark that over the last 4 years, we've never gotten an answer which is no or not enough time. Why? Because there's always enough time. There's always evenings after midnight to work on it. And there are always weekends, which we never fail to encourage you to devote to the RCI last minute effort for that. So we're encouraged by the fact that you've moved on from a cub to a grizzly. And now let's realize what is the true UCLA mascot today. It's Joe Bruin. So you've gone from cub to grizzly to now your average Joe as you go on to become a Joe Bruin at UCLA for that. So we look forward to seeing that. It's going to be hard to replace you at RCI. Why? Because your paw prints as a cub and a grizzly were very large. To fill those paw prints is going to be very difficult for us to assume. But don't worry, we won't forget you. Why? We have installed a tracking device both in your computer and on you, and we won't tell you where it is right now, so we'll be able to find you at any point. Even though you may consider the protection area, there's no protection that's available for this. So when you get that call in the middle of the night, midnight, or on weekends, that's when we preferably try to call you. Just realize when that phone rings, it may be right call calling again. And to make sure that there's no liability for this, of bringing you in as an outside consultant, we have declared for Northern California that you are now the honorary co-chair of RightCare Initiative, so that we now have a legal, and we can cover it with liability because we have that for you. You will not be lost. You will be not forgotten. And we look forward to great success when you come back and join us and replace your honorary co-chair as actual co-chair of RightCare Initiative in the future. Thank you very much.
Thank you.
Say that Flo, who is a real coach for our Los Angeles RightCare University Best Practices, was one of the physicians that interviewed Brian Bong for his UCLA medical school. So the RightCare arms extend far and wide, and we have a lot of people who want to speak. I think we'll go to Dr. Ivy and then Dr. Flynn, and perhaps some of you can grab a glass of champagne for a toast.
Well, I don't have my glass here, but I just want to run down just a few more Brian accomplishments from his work with Amanda on the health coach curriculum, where we went from sort of general health coaching to hypertension health coaching. Brian's hands were on that, from both working on the manuscript about the success of the San Diego RightCare initiative on acute MI reductions, to his creation of briefs that would parallel that, to many, many iterations of pocket cards that I did, Bill, do quite a bit of editing at 3 a.m. with him on font sizes and color schemes, etc. So he has spent an awful lot of time up in the middle of the night when I felt like things needed to look perfect for the next day. He was always willing. And I'm just so pleased, Brian, to see you going into medicine and to know that you're going to be making a difference on health disparities. So I'm very proud of you. Thank you.
Thank you.
We'd love to hear from Dr. Flynn and then Dr. Sky, if we may.
Certainly. Brian, short and sweet, as we say in the Navy, fair winds and following seas. It's been a pleasure, and go Bruins.
Go Bruins.
Good team.
Brian, it's been a pleasure working with you, and being someone new to the RightCare around the time you came. I didn't realize how special I had it being able to work with you, but obviously I recognize that now. Hopefully you've saved a recording of today so that 3 a.m. when you're a third-year medical student and someone doesn't care who you are or what you've done, you'll be able to remember. You'll be able to remember that you were somebody someday, you were somebody, and you'll get back to being somebody again soon enough. So, thanks, Brian.
Thank you.
We have quite a few leaders with us. I see Dr. Wanacott joined us from Lake Tahoe. And Dr. Stock is back on. Dr. Wanacott, how about if you go next?
Well, you know, I had meetings that precluded me from a bunch of these activities, but I said the one I have to get on is between 6 and 6:30, so I can hear all of this. And it's great. Brian, it's been great working with you, and it'll be great working with you again someday. So we'll save you a seat. So good luck.
Absolutely. Thank you so much.
Dr. do you want to weigh in? He may not be able to hear me. And Dr. Stock, did you want to say anything before we do our toasts?
Yes, Hattie. Hi. So I'm in the parking lot right now. So Brian, I'm hearing myself talk, so it's I don't know whether it's happened, but I want you to know that you are so special. And the first time that I met you was at the UC Berkeley, one of the meetings with Hattie, and I was just so impressed how together you had and how you were leading the meetings. I honestly didn't know that you were a student at the time. I think you had just finished one of your courses. Is there a way to get me to stop hearing myself? No.
Dr. Stock, perhaps we could have one of our staff members work with you offline, giving you some technical assistance. Kathy Yarashevich, would you please call Dr. Stock? And Evelyn, if you would please mute yourself, perhaps she can help you work out the technical difficulties so that you can really speak from the heart without feeling disrupted. So we have quite a few UC Berkeley staff members. We also have not heard from everyone on the line. So feel free to, panelists, unmute yourself if you want to weigh in.
So Brian, Dr. Yu here. I graduated from UCLA Med School, so I'm a Bruin. I just want to say that I applaud your decision on the choice of medical school to get your degree. We're in good hands, and we know we can expect great things from you. And then just want to extend during your journey, if there's anything that you need that we can help with, feel free to reach out to me. I think given your record, success is already a given. However, if there's anything we can help with your journey throughout in terms of giving some perspective with what you're going to do, feel free to outreach, and congratulations. Couldn't be more proud of you. Thank you.
Thank you, Dr. Yu.
Brian, Bob, Trang here. Rarely do I get a chance to get to know someone who's both so competent and so affable, and look forward to your coming down here to LA. Once we're able to do it, we'll have to get together. Maybe we can teach you how to surf.
Definitely, absolutely. Thank you, Bob.
So I think, well, I think it's only fair that we wait for Dr. Stock to be able to get her audio working. She's been working so closely with Brian the last few years. And I'll just say that, you know, Brian is when we first met him, I have to say he was extremely shy. And he was, you know, he was a very young student. He was actually a sophomore when I met him at Berkeley. And it's just been a joy to get to know him over the years, while he's really grown into a very confident and well-spoken young man with so many more talents in this period of such fast growth and maturity. It's been really a joy to see Brian's infectious smile appear about 2 years ago. That might have been when you reconnected with Callie at one of our Stanford RightCare meetings. His girlfriend from, was it Bible study when you were in First grade?
Yeah, we had Vietnamese Sunday school together. Very long time ago.
So they're the second Right Care couple after Carla and Michael Pollock, who've just recently moved to Ireland. I see we might have Dr. Evelyn Stock back, but it's a wonderful growing Right Care family, and we're looking forward to your every success as you go forward. And here's Dr. Stock back to say one more item before we go to a toast for our dear Brian.
All right, can you hear me?
Indeed, yes.
Okay, great. So I want to say that for me, Brian has been one of the pillars of the Right Care Initiative, next to Hattie and next to the rest of the staff. You have been so inspiring and gotten me to, oh, I still hear myself, but I just want to say, Brian, good luck with everything. You are part of us here at UCSF at Right Care Initiative. We feel you like families. Thank you for everything.
Thank you, Dr. Stock.
So I know a lot of people need to wrap up. Dr. Sky last evening was telling me about the intensive number of cardiovascular events that are coming into Travis Hospital. And so we really appreciate, Dr. Sky, that you've stayed on with us this long and how closely you've worked with our team, sort of never failing us, no matter how busy you are. So, you know, in addition to our wonderful staff that is very well trained now by Brian, we have very dedicated leadership. And I'm quite sure that all of us are willing to help you along your way as you need. And we will miss your infectious smile. Dr. Sky, did you want to say something? You're muted. You are muted, Joe.
Brian, you're going to have a great time in medical school, and I'll end with one rhetorical question. I'll look forward to finding out how your housing situation worked out, and whether you can pull off the virtual house for 4 years.
Got to be flexible.
Yeah. You can explain that, whether in a couple of years you can tell us whether it worked or not. If it didn't, then don't ever mention it again.
I have a lot of friends in Los Angeles, thanks to many years of Right Care work down there. So if you get in a pinch, you just let us know, and we have a lot of resources to bring to your aid if need be down there. So with that, I would just like to say, bless you for all that you've done and all that you will do to make the world a better place. And cheers. Stay in touch. Keep smiling.
Thank you.
Cheers. L'chaim. Good job, Brian.
Cheers, Brian.
Cheers.
Cheers, Brian. Cheers, Brian. And for the first time ever after a Right Care meeting, you have the rest of the night off.
On that note.
No 3 a.m. calls.
Please send us a picture with your parents and your award. Okay.
I can do the award. I cannot do my parents.
Are you no longer up north?
No, I'm still with my parents, but they're occupied and not at home.
Okay, all right. Well, at
some
point you'll be able to send us a picture.
Yes, I'll be able to send you a picture with. Yes, I will send that in an email.
Yeah, and the one thing we've learned along the way is those clear glass stars do not photograph well. So I apologize, for that complexity. But anyway, our whole loving RightCare family sends you off with all good wishes. Thank you for all, and safe travels.
Thank you. Thank you so much, everybody.
Congratulations and
Oh,
good
yeah.
night, everyone.
Good night.
Good night, Brian. Congratulations.
Thank you.
Best of everything.
Thank you.
Well done.